So welcome back. In the previous classes I was talking about the higher order sliding mode control, and somehow higher order sliding mode control is equivalent to the output regularization problem in presence of the disturbances and uncertainties. And one of the obvious requirement whenever we are going to design the control, I need the output and their higher order derivative. So how to get this derivative? So for that we have two different kind of solution. One solution is called observer, another is differentiator. So in this lecture we are trying to understand the difference between the construction of differentiator and observer. Obviously these two things are coming from the same literature, that is based on the Leuenberger observer. So we are trying to understand that how basically Leuenberger observer lends to the classical differentiator, and after that we are going to extend it for the high gain based differentiator. First foremost I am going to answer this question: why differentiator is required for the sliding mode control. Okay, so we have already seen that if I have some kind of system that is represented in the output regularization way, so I have minus C and C is here, and after that we have Km and K capital M into U, and I have to design some kind of discontinuous control based on the principle of homogeneity such that I can able to maintain sigma and sigma dot equal to 0 in some finite time t greater than equal to t, and after that we have to maintain it. So one of the obvious choice for this is K1 signum sigma minus K2 signum sigma dot. Now most of time whenever I have plant like x dot equal to fx plus gxu, and using input output linearization basically about x or output equal to sigma, whatever you want you can represent it. Basically we are trying to generate the control. So information of sigma is available, but information of sigma dot that you have to construct. So if you have exact mathematical model, then construction of sigma dot using observer is very easy. You can apply the Leuenberger observer if there is no disturbance. But most of time what we are assuming that since I have nonlinear system, so obviously this nonlinear system is affected by the disturbance. So one of the way you can construct some kind of differentiator such that you can obtain sigma dot from the measurement of sigma. So one can able to go via numerical differentiation technique, but numerical differentiation technique will not work because most of time the measurement of sigma which is coming from the sensor containing some kind of high switching frequency noises, and if you differentiate that high switching frequency noise with very small amplitude they have, but during differentiation that become very much dominated, and in this way you cannot able to get the exact information of sigma dot or even if approximate information of sigma dot, and due to that is a numerical differentiator we have to avoid. So what is another solution? Other solution is differentiator or observer. Observer is also several time that will not work because system model is not known. We are just assuming that I know the relative degree of system, that is 2, but mathematical model is completely unknown, means I have black box kind of situation, and due to that reason we have to go via the differentiator, and due to that reason Professor Levant also proposed arbitrary order differentiator, and they make sure that that kind of differentiator will work in presence of the uncertainty or some kind of measurement noise. So you can able to see that high gain observer or high gain observer based differentiator is also able to provide us sigma dot up to sigma r, but their differentiation process is actually asymptotic in nature. It means that I have to design finite time controller but whatever differentiator I am going to use, that is asymptotic, and due to that reason that is somehow not matching, because differentiator should be more faster than the controller. That kind of requirement whenever we are designing control based on the differentiation process. So now what is key outcome? So key outcome that is required whenever you are going to implement the sliding mode control, or particularly higher order sliding mode control, whatever differentiator you are going to select, that maintain finite time convergence in the presence of the measurement noise. But in this lecture I am just going to give you the foundation stone how basically differentiator design comes into picture. Okay, so at least I am assuming that in absence of the measurement noise, how to differentiate some kind of signal. So you are already familiar with the Leuenberger observer. So this is nothing but some kind of linear time invariant system, LTI system, and here I am assuming that this mathematical model is completely known. So how to design Leuenberger observer? You can just copy the dynamics. So I have copied the dynamics, and due to that reason I have written here x cap, a x cap and bu, and this is nothing but some kind of correction term that is based on the output information. Okay, here I am assuming that output is already known to us, and this is the estimation of output, that is c x cap. Finally error dynamics comes into picture, and if you maintain A minus LC stable, it means that if you design L such that this matrix, all eigenvalue of this matrix is somehow lie in the left half plane, then you can able to maintain this kind of observer. And what is the responsibility of this observer? Finally it is possible to show that E equal to 0, and what is E? E is nothing but xt minus x cap or x cap minus xt. Based on the definition you can able to write both is okay, and based on that here plus and minus sign comes into picture. So E tending towards 0 means x equal to x cap. Now from this particular Leuenberger observer you can see that one can also able to generate the idea of differentiator. Okay, so what is basic idea that is suggested by Professor Leuenberger? That since you don't know the dynamics, because most of time whenever we are solving higher order sliding mode control, our dynamics is lie in black box, and due to that reason you can keep A equal to 0 and B equal to 0. So if A equal to 0 and B equal to 0, so you can see that these two terms will not present. So finally I have a structure like this. Now here you can assume, since that you have single input or single output, since I have to just differentiate one signal at a time, and therefore this assumption is actually quite reasonable. Okay, so let us again come back to the original slide. So now here I have assumed C equal to 1, and if you keep L is very large, so now C equal to 1, so y hat is equal to x hat, and now if you differentiate, then this system comes into picture. And I am going to show you that if you select L, that is very large, then you can able to construct the derivative from this particular differential equation. You can also able to generate the higher order differentiator by cascading this structure. Okay, so you can see here that z1 dot equal to z2 and lambda y minus z1t, and whenever you are cascading second, then you can able to use same kind of information. Okay, and in this way you can able to construct any order of the differentiator, nth order differentiator, and z1 is going to estimate yt, z2 is going to estimate y dot, and in this way you can able to get some kind of nth order differentiator based on the high gain observer. It means that lambda 1, lambda 2 up to lambda n you have to keep high. So let us first establish why this will works like differentiator. So since this is linear system, and due to that reason what I have done, we have taken the Laplace transform, and after taking Laplace transform and assuming initial condition equal to 0, and after adjusting, you can see that this kind of structure comes into picture. Now, what is meaning of derivative? Derivative is nothing but s into y cap s. So, in this structure, easily you can able to see that if lambda is very high, then what happens? Here y dash cap equal to s into ys, that is nothing but the differentiation of the ys. In this way, by keeping high gain, I can able to convert Leuenberger observer into differentiator where a and b both equal to 0. Similarly, I can able to prove for any higher order. Okay. Now, it is possible to show that this kind of differentiator is highly sensitive to the noise. So, here I have taken some kind of noise. You can free to select white Gaussian noise, and we are trying to understand the effect of noise whenever we are trying to develop some kind of differentiator. So, this is the equation. Again, what I have done, we have keep a and b equal to 0 in case of Leuenberger observer. At this time, whatever measurement quantity yt that is affected by noise, so that term also come into picture. Now, I have to design L such that I can able to get differentiation. Okay. But here if you see the dynamics, so basically if L is the gain, high gain, so our overall dynamics is highly affected by this particular gain, because L I have to keep very large. We have already proved here that under which situation observer will work like differentiator. So, only condition that if lambda is large, then only I can able to approximate left hand side by some kind of term, that is s into ys, and s into ys is nothing but in time domain, if you will look into that is the differentiation of the y dot, and due to that reason it means that whenever noise comes into picture, this differentiator will not work. And there are several methodology to mitigate the noise effect. So, one of the methodology, you can pass yt with low pass filter, and this will actually reduce the high frequency noise, because high frequency noise is going to create problem here. Okay. And obviously L gain should very high, but you have to somehow balance. Okay. And another option, that is very exciting option, is sliding mode differentiator, that is proposed by the Professor Utkin as well as Professor Levant. Obviously accuracy of the Professor Levant differentiator is very high, because that is based on the higher order sliding mode control. Another option, you can able to utilize the Kalman filter. Okay. Another way to handle that differentiation, people are telling that you can use this kind of term. Okay. But what is the main intention of this course? That we are trying to understand the sliding mode differentiator based on the first order sliding mode control as well as on the higher order sliding mode control. So, in this lecture, first I am going to introduce differentiator based on the first order sliding mode control, that is proposed by Professor Utkin. And obviously, whenever you are proposing some kind of differentiator, so you have to give performance matrix in presence of noise. Similar kind of matrix you can also able to see in case of the differentiator based on higher order sliding mode control. Okay. Obviously language is different. So, here we are talking in terms of the mean square error, that is defined like this, signal to noise ratio, that is defined like this, or root mean square in this way. Okay. So, in this way people are comparing the performance of the high gain based differentiator or sliding mode differentiator. Now, this is the idea of the sliding mode differentiator, and obviously Professor Utkin is no more now, but he has several contribution. We have already seen that he has contributed on the theory of chattering, theory of on-off control, after that theory of integral sliding mode control, theory of differentiator. So, everywhere, almost every places Professor Utkin has contributed, and due to that reason now sliding mode is well established. Okay. Now here you can see that what is idea of the Professor Utkin, that in order, suppose that if you have to calculate the derivative of this signal ft. So now you can generate some kind of sliding mode control by defining xt equal to ft minus xt, and you can take the derivative. So f dot comes into picture, and whatever x dot, that you can replace by vt, and vt is nothing but m signum xt. So somehow you can think like this, that I have some system like x dot equal to u, and u I am going to design, that is nothing but somehow m signum xt, something like this. Okay. Now if you design sliding surface like ft minus xt, ft is the signal which you want to differentiate, and xt is nothing but that is coming from this system. Now s dot dynamics, if you see, then that is f dot minus m signum st. Now if you keep the value of m that is greater than the value of differentiation of ft, then it is possible to show that sliding mode comes into picture. And once I have sliding, so obviously xt equal to 0 in finite time. So for all t greater than equal to t, and that is also going to maintain. So once xt equal to 0, it means that value of xt is completely equal to the ft. And what is interpretation of the equivalent sliding or sliding equivalent, that s dot also equal to 0. So s dot equal to 0 means average value of the vt, this discontinuous term, that is exactly equal to f dot t. So average value is going to estimate the form of derivative of the ft. That is the clear cut idea based on the first order sliding mode control. And now you can see that here only condition, that whatever signal you are going to differentiate, their derivative should bonded. If their derivative is not bonded, then actually you cannot able to apply the sliding mode control, because in order to occurrence of sliding mode control, m should be greater than equal to the derivative of the disturbance. M you can able to select very high also, because differentiator system is running inside the computer. Okay. So no actuators or nothing physical circuit is required in order to get the differentiation of some signal. Okay. So same kind of things I have written, due to equivalent sliding, okay, means S equivalent or S dot equivalent, sorry, S dot equivalent, that should be 0. So if you pass the M signum S through the low pass filter, then what happens? Finally I can able to reconstruct the disturbance, and that is the analytical conformation S equal to 0, and S dot equivalent value exact S dot not equal to 0. So I have to filter out the high frequency component. How to filter? So you have to design low pass filter. So accuracy of differentiator is based on the accuracy of filter design now. Okay. So now you can see that I have constructed first order system, because I have to construct differentiator based on x dot equal to u. So due to that reason this block comes into picture, and after that what happens, I have to apply, I have to differentiate this signal ft. So I am going to take the difference between xt, ft minus xt, that is nothing but sliding mode control, and after that I am going to pass this with some kind of switch gain based control, and value of gain is m. And then whatever output that comes into picture, if I pass through the low pass filter, this is the frequency domain equivalent of low pass filter, and if tau is very small, then exact value of zt equal to f dot t. Okay. So final problem, how to design the time constant of the filter. Now similarly you can able to cascade this structure, and then you can able to get any higher order derivative. So that is also equivalent to the observer design by Leuenberger. I have already told you that how basically differentiator design comes into picture. That is nothing but the obvious consequence of the Leuenberger observer. You can keep A and B equal to 0, L gain you can keep very high. Okay. Now, by cascading this structure, you can able to calculate the higher order derivative also. So, suppose that first derivative of signal is x2, and at that time you have to design system like this. Okay. So, x1 cap dot Vt is m gain, and this is nothing but the sliding surface you have to define, and after that you have to whatever z will comes into picture. So, z is nothing but, from this diagram that become clear, that whatever V you can going to enter here, and Z is the output of filter. So, same kind of things I have written here. Okay. And finally, what happens? Z is nothing but exactly equal to x2. Now, again x2 you can pass here, and after that you can able to generate the second derivative. So, and second derivative is nothing but the x3. So, suppose I have signal ft. So, first derivative is x2, second derivative is x3. So, in this way one can able to do. So, I will get ft here, f double dot here, and f dot here, f double dot here. Okay. So, every time you have to design the filter. It is not difficult to understand this whole construction, just I have to actually understand that how basically this dynamics is cascaded. So, if you write the program, or you can use the block diagram like this, in this way you can able to construct any order derivative, but every time you have to become very careful, because I have to design the gain of or time constant of the low pass filter. Okay. So, first time constant should very fast, because whatever first derivative that is substituted to second derivative. So, there exists some kind of relation between tau 1 and next tau 2. Okay. So, you have to select tau 1 that is more faster than tau 2. In that way you can adjust, and you are able to get any order derivative. Now, another important thing, that is the observer design, because everything is consequence of the observer. So, in this lecture I am also going to extend one more concept. Suppose if I have mechanical system, so how to get the q dot by the information of q. So, I have two options. If q is there, I will design some kind of differentiator based on the Woodkins, or obviously high gain feedback. High gain feedback I am going to avoid, because that will just provide us the asymptotic stability. But whatever differentiation process that is given by the Professor Woodkin, you can see that is going to converge in finite time. Why? Because differential process here due to the first order sliding mode control, and obviously first order sliding mode control is going to occur in finite time, and due to that reason after finite time we start getting the derivative, and due to that reason this kind of derivative I can able to utilize for the higher order sliding mode control design. Now, another way I can also able to design some kind of finite time observer. So, I have second order mechanical system, and we also know the super twisting algorithm. And what is the structure of super twisting algorithm? You can see that structure is second order, but everywhere in this particular structure second term that is just containing the information of the x1. So, here I have information of x1, and here also I have information of x1. So, if I have some kind of system like x1 dot equal to x2 and x2 dot equal to u, so I can add correction term that somehow looks like this, or second correction term like this. In this way whole structure is converted like the super twisting algorithm, and finally I will get x1 equal to 0 and x1 dot equal to 0, and in this way I can able to estimate the information of x1 from x2. So, that kind of things we are going to look into. So, most of the mechanical system, particularly that is Euler-Lagrange system, that is basically represented by this, and this system several times I have talked, and you can see here that I am also assuming some kind of uncertainty term I have, and tau is nothing but generalized torque. Now, one can able to represent this system by second order dynamics. So x1 equal to q, x2 equal to q dot, and u equal to tau I have actually taken for this particular second order system. And then I have very nice structure, state space structure for the second order system, and this is nothing but the uncertainty. Okay. Now what I am assuming, that this uncertain part is obviously I have to generate some kind of condition such that I can able to get the measurement of x2 from the measurement of x1. So that condition I will discuss after some time. Okay. What is the assumption? We are assuming that Mn, so let us come here. So M, C, P and G all are known, so that kind of assumption I have. So this represent the nominal model of this. Okay. So now if nominal model is known to you and if this is original one, then whatever extra part that I am going to absorb here in form of zeta t, x1, x2 and u. Now I am going to construct the observer. So how to construct the observer? Whatever things is known, you can copy it. So x1 and x2 I am going to copy. This term I am assuming that is actually known, and due to that reason during copying process I have copied it. Okay. But this term is completely unknown, and due to that reason I am not going to copy it. And here you can see that I have written x1 because I know that y equal to x1. It means that x1 is known to us, and due to that reason I can assume that either I can write x1 cap here or x1, both are exactly the same, and z1 and z2 are nothing but the correction term which we have to design. So this is the structure of the observer which is running inside the computer. Now how to design the correction term? So correction term I am going to design based on the super twisting algorithm. Okay. So you can see that inside super twisting algorithm I have some kind of form like half signum and x1 is here, but here I have actually write in form of the error, because finally what is our goal? I have to maintain error equal to 0. So I have defined x1 tilde as a error between x1 and x1 cap, x2 tilde as the error between x2 and x2 cap. And now you can see that overall algorithm is exactly converted into same like the super twisting algorithm, and we have already proved the convergence of super twisting algorithm. This term L alpha is capable to take care about any kind of uncertainty that is going to lie here. And how basically we have defined, that is the difference between these two. Since after once observer is actually converge, at that time this and this is exactly equal, because x2 equal to x2 cap. So primarily this term comes into picture. Okay. Now if this term is upper bounded by f plus, and if you select gain like the Professor Levant has suggested, so it is possible to show now that both x1 tilde and x2 tilde equal to 0. So it means that I can able to estimate x1 and x2. So I can able to design some kind of twisting controller or other kind of controller, okay, or higher order controller. Now one of the important thing here, since we have here discontinuous term, so it is possible to show that in this process x1 tilde equal to 0, x1 tilde dot also equal to 0. That is the beauty of the super twisting algorithm, that whatever term, that term and their derivative equal to 0. So equivalent value of x2 dot tilde is also equal to 0. What is meaning of equivalent value equal to 0? It means that alpha signum x1 tilde is exactly going to recover this part of uncertainty. Okay, and that kind of idea you can able to utilize here in order to construction of the uncertainty. It means that suppose you have some kind of plant, and initially that plant is running, and if some fault come into picture, using this observer easily you can able to understand the fault and what kind of fault is going to enter. That fault also you can able to estimate. So here observer can use as a fault detection process also, and that is also called equivalent output injection, that using this kind of philosophy I can able to estimate what kind of fault is basically inside the system. So basically whenever we have this system, so I can able to decompose this as a internal uncertainty as well as external uncertainty, and most of time fault is coming from the external source or some kind of attack is coming from external source. So easily you can able to get that attack or form of signal which is attacking to your system by passing through the low pass filter. Again tau if you design, and you can see here that is the guidelines of selection of tau. So time constant of filter that should lie between less than 1 and greater than should be the sampling frequency, because most of things are running inside computer and due to that reason sampling comes into picture. Now if you have nominal model, then obviously this part delta f that equal to 0. So now it is possible to show that Z equivalent is exactly equal to eta. Now in this way you can able to identify the perturbation or identify the fault or identify the attack. Okay, so how basically you are interpreting perturbation, that depend on the practical situation. So what we have done, we have taken the pendulum system. So pendulum system is represented by second order. We have also discussed the mathematical model of pendulum, and here I am assuming that we have uncertainty. So this pendulum is hanging in the free air, and after that now what is our goal? Suppose that if I know x1 equal to theta, so I have to estimate theta dot. So for that we have designed the observer that is based on the super twisting algorithm. So this is nothing but some kind of higher order observer, and again their work is exactly same like the differentiator, because here if you are going to measure x2, so somehow you are going to measure x1 dot. Okay, so purpose of observer and differentiator for particularly this class of problem is exactly same. Okay, but again I am going to comment that if you know the model, then you can design the observer, but if you don't know the model, then only you have one choice, that is differentiator. Okay, and after that we can able to calculate the again Z1q, that is equivalent gain by passing through the low pass filter. You can see here tau I have selected this, and this is the simulation result. So you can easily able to estimate the disturbance. Okay, several places nowadays systems are running on network, so disturbance estimation or fault estimation is very active area of research. So there you are able to run one extra loop inside the computer along with your plant, and whenever attack will come, so using super twisting algorithm, if you have second order system, easily you can able to estimate. Similarly for higher order, you have a choice of the arbitrary order differentiator that I am going to discuss in the next class. Okay, so what is conclusion? So in this lecture, first we are trying to understand how basically observer leads to the differentiator. So I have started with the Leuenberger observer. After that what we have done, we have created some kind of differentiator based on the Professor Utkin philosophy, and then we come to the observer, and then we have simulated the system. And what kind of conclusion we have seen in case of practical system, that pendulum dynamics is modeled in a state space, and due to that reason here you can able to prefer observer over the differentiator. Okay, and one can able to also get the equivalent value of fault just by somehow output injection term. Okay, and using low pass filter I can able to calculate that particular value. So with this remark I am going to end this lecture. Thank you very much.